Hi everybody, my name is JC. Welcome to my game engine series. This episode is called Vulkan in a nutshell. Today I'll be providing a grand overview of the Vulkan API. Enjoy! If you've done a Vulkan tutorial before some time ago and need a refresher, or if you're new to Vulkan and want to see what this graphics API is all about, then this is the right episode for you. Today we will provide an overview of all the key concepts in Vulkan. We will talk about how all Vulkan objects are connected, how they interact with each other. We will also be introducing some basics about how to render a 3D scene in general, so basics about computer graphics in general. We will introduce a lot of terms that are either about computer graphics or specific to Vulkan. And then I'll be injecting some references to my game engine Lucre so that you can look at some example implementations. We have a lot of ground to cover today, so let's dive right into it. The central question of this episode is, how do we render a scene with Vulkan? We need obviously a 3D model, a window on a monitor, and we want to harness the power of the GPU to render a scene. To load 3D models, we can use GLTF. This file format is based on JSON and it supports 3D models, including animations. It can also be used to describe entire scenes, including a scene graph hierarchy. GLTF is an open and versatile format, and it is very well supported by Blender. Now, our game engine Lucre also supports OBJ wavefront, but that's more out of a legacy. So GLTF is the 3D file format that we are using going forward. Then we create a window with GLFW. GLFW is a small cross-platform library written in C. It can be used to create and manage a window on your desktop, be it on Linux, Windows, or Mac. There are also other cross-platform libraries to accomplish this task, such as SDL2 or SFML. What they all have in common is that they can provide a Vulkan surface we can render into. To get a hold of the GPU in our application, we can create a Vulkan instance. This instance has information about all the available GPUs on our computer. It lets us pick a physical device, and from that physical device, it lets us create a logical device. The window that we just created with GLFW is shown on our monitor, which has a certain refresh rate. This could, for example, be 60 Hz. 60 Hz means that we get a vertical sync pulse every 16.6 milliseconds. With this vertical sync pulse, or short VSync, the content of the window is refreshed. So our application and the GPU need to provide a new frame every 16.6 milliseconds to the Vulkan surface of the window. Back to the Vulkan instance, which we said lets us pick a GPU and create a logical device called VK device. Here's the code to create the instance. I'm showing this because it's typical Vulkan code. Down here, we have a call to a library function vk create instance. We pass a Vulkan structure, in this case here called create info. This structure is referencing another structure, app info, which we create up here. So then in this call, we pass here a null pointer, and then the instance we need this function to initialize, and then we check if it was successful or not. Now back to our original question, how do we render a scene with Vulkan? So far we have a window that has a Vulkan surface called VK surface KHR. We have a logical device referred to as VK device that represents the GPU, and we can load 3D models in the GLTF format that we, for example, can export from Blender. Now we can also use shader programs on the GPU. Shader programs are written in GLSL and they are compiled to SPIR-V. SPIR-V stands for Standard Portable Intermediate Representation V, and our game engine Lucre has a built-in compiler for that, referred to as shader-C, in the file engine platform Vulkan vkshader.cpp. So, where do the shader programs go into? In our case, they go into the graphics pipeline. Vulkan also offers other pipelines, such as a compute pipeline or a ray tracing pipeline. But we're using the graphics pipeline, aka rasterization pipeline, to render a 3D scene. The pipeline has 5 stages. Well, actually there are some more stages, but I omitted the stages for tessellation here. So the stages are, we have an input assembler, then we have the Vertex Shader, we have a rasterizer, the Fragment Shader, and color blending. So some stages are fixed function stages, and some stages are using shaders. I will explain all the stages in detail in a little bit. For now, just note that our shaders always come in pairs. So there's always a Vertex Shader and a Fragment Shader. In our engine, in the subfolder platform Vulkan, we have vkpipeline.cpp and .h to represent a pipeline. So here we have a class vkpipeline, which exposes a function to bind this pipeline, then to create a default pipeline configuration info, and to set the color blending state. So this function here, default pipeline config info, sets up some sensible defaults for the fixed function stages. So this here is used to configure the graphics pipeline or just set up some defaults. And when we actually create a pipeline, we want to tweak some of these defaults. So for example, here we are setting up the viewport. Here we are setting up the rasterization. Here we are setting up multi-sampling, which is used during rasterization. We're setting up here the color blending state, and so on and so forth. So this is how it looks in our engine, and this is how we configure a pipeline, or how we at least set up some defaults for the pipeline that we can then tweak later. The first stage of the graphics pipeline is the input assembler. It is retrieving vertices from a vertex buffer. The input assembler stage retrieves vertices per primitive, and in our case, we configured the stage to use triangles as primitives, so it retrieves 3 vertices at a time and forwards those to the Vertex Shader. Now, what is a vertex? If you look at this 3D model here of the bunny, its mesh is comprised of triangles, whereby each triangle has 3 vertices. But a vertex does not only have a position or a 3-dimensional position, it can also have other attributes. So these attributes can be freely configured in Vulkan. Other examples are here a color per vertex, or a normal vector, which is a vector perpendicular to the plane the triangle lies in, or it could be UV coordinates, which are texture coordinates and which are used if you want to map a texture to each of the triangles of a model. The next stage of the graphics pipeline is the Vertex Shader stage. It is used to transform vertices. Per invocation of the Vertex Shader, exactly 1 vertex is processed. The most common transformation that is applied in the Vertex Shader is the Model View Projection Matrix, or short MVP matrix. This is a 4x4 matrix that is the result of multiplying the model matrix, the view matrix, and the projection matrix. So what are those matrices? Now, the model matrix is used to place a model into our scene. When this model comes out of Blender, for example, it comes with a certain scale, it has its own origin, and we need to place it somewhere in our scene. So for that, we scale it, rotate it, and translate it, and that can be expressed with a model matrix. Then we need a camera to look at our scene. This camera can be expressed with a view matrix. It has a look at direction, it has a position, and it has a zoom factor. And lastly, we need to project our virtual 3D scene onto a 2D window, right? Our monitor, basically. So for that, we're applying a perspective projection, which can be expressed in a projection matrix. So all these 3 can be multiplied together, and then we have the MVP matrix, and this is what is applied in the Vertex Shader per vertex. Then the output is 1 intrinsic variable, which is called GL _position, which is a vec4. So this is a vector with 4 elements. The first 2, X and Y, are the position on the screen, in-screen coordinates. And the third one is the Z coordinate. It's a depth coordinate that can later be used to perform a depth test and to see if anything is in front of the model. So in this case, the Fragment Shader does not have to be called. And the 4th element of GL position is a scale. So after the Vertex Shader stage and before the rasterizer, the first 3 elements of GL position will be divided by this scale to normalize the coordinates into normalized device coordinates, which go in the x direction from -1 to 1, and in the y direction also from -1 to 1. There can also be user-defined output from the Vertex Shader stage. Before we said a vertex can, for example, also have a color or a normal or UV coordinates. So those three here would have to be passed down to the Fragment Shader. Then we said the input assembler is taking 3 vertices corresponding to 1 triangle and calling the Vertex Shader then 3 times. So then when the rasterizer is called, which is the next stage, the third stage of the graphics pipeline, the rasterizer will figure out which screen pixels correspond to this triangle, and for each pixel it will call the Fragment Shader. Now, the values in the Vertex Shader that were provided for the 3 corners of the triangle, in this case here color, a normal, and the UV coordinates, they will be interpolated for all pixels. So for example, for the UV coordinates, we have, if we want to do this pixel here, right in the middle, between these 2 vertices here, it will be a linear interpolation between the UV coordinate of that vertex here and this vertex. Or if we were using this color here in the Fragment Shader to shade the pixels, and let's say this color of this vertex here would be red, and this would be blue, and this here, then from here to here it would be a gradient. So there is one invocation of the rasterizer per triangle. It determines which fragments fall into the triangle and calls the Fragment Shader. Actually, before that, we can configure a depth test. If another fragment is closer to the screen, the Fragment Shader does not need to be called, because we know that the current fragment is obstructed by a different fragment. If the current fragment is the closest to the screen, its z-value will be written to the depth buffer and the Fragment Shader will be called. The Fragment Shader stage is the 4th stage of the graphics pipeline, and here we apply color, we apply lighting, shadows, reflections, etc., etc. To our scene. Some terms I want to introduce here. Models often come with a texture that is referred to as a diffuse map or albedo map. So that is just the base color. Then we have other maps that also come with models. For example, a normal map. So this is a per pixel surface normals. So that has a higher resolution than just the normals that we have in the vertices. So a normal map can be used to apply more fine-grained surface nuances to a model without putting too many vertices into this model. And yeah, then we have another term that I used before, UV coordinates. So these are coordinates, texture coordinates from a map or from an image, so that we, per triangle, can use a sampler in the fragment shader and sample from those images according to those UV coordinates. The final stage of the graphics pipeline is the color blending stage. It is called per fragment. This stage will blend the output of the fragment shader with the existing color at the location of that fragment in the output image. In general, the color is defined as a vec4, whereby the first three elements are red, green, and blue, and the fourth is an alpha value. All these values here can be between 0 and 1. Now, we can freely configure the blending function. However, the most common blending function is to take the new color or the RGB values of the new color that was calculated by the fragment shader, multiply it with the new alpha value, then take the existing color from the output image and multiply that with 1 minus the new alpha value, and add those two new colors together. Now that we know how the graphics pipeline in Vulkan works, the next question is, how are graphics pipelines organized? The answer is, they go into renderpasses. To draw a frame, we need at least one render pass, but there can also be a sequence of render passes. And then a render pass can also be divided into subpasses. So in the example here, we have 3 render passes per frame, a shadow pass, a 3D pass, and a 2D pass. And the 3D pass is subdivided into one subpass for geometry, one subpass for lighting, and one subpass for transparency. Then in this example, we have 2 models here, a teapot and a bunny, and a monkey here. So these 2 here on the left, we want to draw with pipeline number 1, which we also call material 1. So this material has this monochrome look. The shader here takes the color from the vertex. Pipeline 2, or material 2, is applying a texture to the model, so it has a different shader pair. So after the shadow pass, when the 3D pass starts, we will bind pipeline 1, then we will bind the vertex buffer of the teapot, and we will issue a draw call to pipeline 1. Then we will bind the vertex buffer of the bunny, issue another draw call to pipeline 1. Then we need to bind pipeline 2, the vertex buffer of the monkey, and issue a draw call for pipeline number 2. So all 3 draw calls go into the same subpass, which is referred to geometry subpass, in the same render pass. Yeah, so this is how graphics pipelines are organized. They always go into a render pass, and they can go into a subpass. Per subpass or per render pass, multiple pipelines can be drawn. Now on the CPU side, or in our application, we organize the graphics pipelines in so-called render systems. So in the folder engine platform Vulkan, there is a subfolder called systems, which is dedicated to render systems. So let's take a look at one of these systems here, for example. This one is called PBR diffuse system. This system has a constructor that takes in a render pass and a list of descriptor set layouts, and then it has a public function to render entities, which takes in a frame info structure, and it takes in the registry of our scene. Now this render entities retrieves a view to all components in our scene that have a mesh, a transform, and have the PBR diffuse material. Then it will loop over all those objects, and for each object it will retrieve the transform, it will retrieve the mesh, and if it is enabled, it will bind the model. So that means it will bind the vertex buffer, and it will issue the draw call. What is important to know, render passes have image attachments. And per render pass, the image attachments always have the same size. So in our example, we said we have 3 render passes, a shadow pass, a 3D pass, and a 2D pass. The shadow pass has one image attachment, which is a depth attachment. It is referred to as the shadow map, and it has a size of 1024 times 1024. Then the 3D pass has multiple attachments, a color attachment, a depth attachment, and some G-buffer attachments, and they all have the dimension 1920 times 1080. Now the 2D pass is using the same color attachment that the 3D pass was rendering into, so this one has also the same dimension 1920 times 1080. Now the question is, how do we get the shadow map into the 3D render pass? So down here we see now another pipeline, pipeline 3, which is the lighting pipeline. So here we have yet another shader pair that is used here in the lighting stage. And this here in the Fragment Shader, it will use a sampler to access the shadow map. So the shadow map that we here created as this depth buffer in the shadow render pass will then in pipeline 3 in the Fragment Shader sampled exactly the same way as we sample the texture. Okay, we covered already a lot of ground, but one link that is still missing is the swap chain. The swap chain gets the color attachment of our render pass sequence to the window on our monitor. But first, you need to understand that there's only one frame rendered at any given point in time on the GPU. So for example, the depth attachment of the shadow pass exists only one time on the GPU. This is also true for the depth attachment of the 3D render pass, and here it's also true for the G buffers. However, the color attachment is a little bit different. The color attachment we get from a swap chain. Now we said the monitor has a certain refresh rate. So with every VSync, we provide a new buffer to the monitor, which is called a front buffer. While this front buffer is shown on the monitor, the GPU can work on the back buffer. So we can either do a double buffering, that we have one front buffer that is shown and one back buffer that we can render into, or we can do a triple buffering. That means we still have only one front buffer that is shown, but as soon as we are done with rendering into the first back buffer, we start rendering into a second one. This is to decrease latency. What happens when the window is resized? So before we said we have a window size of 1920 times 1080, and then we said our 3 images of the swap chain, so we are doing triple buffering here obviously, have the same dimension, 1920 times 80. This is also the dimension of all the input and output attachments or image attachments of the 3D pass and the 2D pass, and only the shadow pass is not affected. Then we resize here with the new size 1650 times 975. So that means the swap chain, the 3 swap chain images, all of them need to be resized. Then also the images of the 3D render pass, the depth attachment, for example, and the G buffer attachments, all of them need to be resized. Then the same here is true for the 2D rendering pass. However, the shadow pass is still not affected because the output of the shadow pass, the shadow map, is sampled down here in pipeline 3 in the Fragment Shader. Another question we need to clarify is, how do we, on the CPU side, with our C++ application, tell the GPU to pull off the render pass sequence, to use certain pipelines, to use the swap chain? And this is where command queues and command buffers come into play. So in the beginning of this video we said we can create a logical device referred to as VK device from our physical GPU by means of a Vulkan instance. Now the logical device will expose command queues for certain applications. So that could be a command queue for graphics or for just transfer, for example. And then we can use a command buffer, so we can assemble a command buffer on the CPU and copy this command buffer into a command queue. On this slide here, you can see an example command buffer. So it says here begin render pass, bind pipeline, push constants. So a command buffer can also take smaller amount of data, such as the 4x4 MVP matrix that we discussed before. Then we can issue a draw call here, and we can say end render pass, begin new render pass. So this is how we create a task list on the CPU and send it to the GPU. When it comes to images on the GPU, we can have either image attachments for render passes, or we can use a sampler in the Fragment Shader to sample textures. The difference is the position in the render pass image attachment is determined by the rasterizer, or when for that position the Fragment Shader is called. So there is no random access for render pass image attachments. However, a sampler in the Fragment Shader can randomly access a texture. And for this, we need descriptors. So descriptors are pointers on the GPU, and Vulkan only allows descriptors to come in descriptor sets. So I'm kind of trying to show here the equivalent in C++. Let's say we have 2 pointers to a texture and 1 pointer to a buffer. So that would be a descriptor set. And then this descriptor set needs to be bound to a pipeline with a certain layout, and then the sampler in the Fragment Shader can use this pointer or descriptor to access a texture or a buffer. Thanks for watching. If you like this YouTube video, please give it a thumbs up. Also, the same for the engine if you can. If you have a GitHub account, please also like the engine. And see you next time.